So what we have here are two demonstrations of angular momentum. Sarah's on a stool that can rotate freely, and so it can turn. What we're going to have her do first is we're going to have her take these two weights and hold them in her hand.
Okay.
So when we talk about angular momentum, it's a lot like linear momentum. Momentum is inertia in motion. So if something's moving, it wants to keep moving. For angular momentum, if something's rotating, it wants to keep rotating. But the big thing about momentum and angular momentum is that they're conserved. That means that the total amount won't change unless there's an outside force, or technically for rotating unless there's an outside torque. So what I'm going to have you do is I'm going to have you hold these right here and go ahead and give yourself a few spins on the stool. Get yourself moving. So once she's rotating, she has a... This wasn't the hard part yet.
Oh no!
Once she's rotating, she has angular momentum, and then spread those out.
Okay.
When she spreads them out, her moment of inertia, that resistance, will increase, and so your speed decreased. When you pull those back in, you spin a little bit faster,
right,
because your momentum can't change. Yeah. So by moving the weights, you're changing the speed that you rotate, because the rotational momentum, the angular momentum, can't change unless there's an outside torque. So when you bring them in, you're lowering your moment of inertia, you spin faster. When you bring them out, you raise it and you slow down, because that total momentum is always the same. What we're going to do is we're going to use this motor and we're going to spin the bike wheel up. And so I'll go ahead and get it spinning. Now this bike wheel has angular momentum. I'm going to give it to you. Okay. And you're sitting still. Go ahead and turn that over. The bike wheel has angular momentum. When we give it to Sarah, her angular momentum is set. But as soon as she turns the bike wheel, there has to be conservation of angular momentum. The total amount can't change. So when she turns the bike wheel, she changes the direction and she starts to rotate as well. Her total angular momentum is the same as when I handed her the wheel, but because we move the wheel, she starts to turn. And if you notice, the wheel is spinning in the opposite direction of Sarah, because when you increase one angular momentum, you have to decrease it the other way. So if you make one of the angular momenta spinning clockwise, then the other one has to spin counterclockwise to counteract that. The total amount can't change. It has to stay the same. And did you feel that resistance to turning it too? Yeah. It's hard, yeah. That's exactly like a gyroscope, because in a gyroscope it has angular momentum, so it resists actually falling over. In this case, it resists being tilted, it resists being turned, because you have to change that angular momentum. So this is the opposite of the demo we did before, where you're starting with a big angular momentum, and I'm going to give you a gentle spin. I'll go the other way.
You're so nice.
And then pull those into your chest.
Oh my gosh.
This is actually the exact same idea that you see ice skaters use. When they start a turn, when they start a spin, they have their arms and their legs out so that they can give themselves a gentle spin, and then they bring that all together, they decrease their moment of inertia, and they start to spin faster. Do you want to give me a good spin?
You want to go this way?
Sure. I already am. The closer they are to the center, the smaller the moment of inertia.
Wow.
And the more noticeable that change.
Yeah.